An explosive phase transition model challenging mass energy equivalence and relativistic interpretations. By Joseph George. The concept of the mass defect, central to nuclear physics, is traditionally interpreted through Einstein's mass energy equivalence principle, E=mc², which posits that mass can be directly converted into energy. This principle is fundamental to explaining the energy release in nuclear reactions. In atomic nuclei, the mass defect represents the difference between the measured mass of a nucleus and the combined masses of its constituent protons and neutrons. This discrepancy is typically attributed to nuclear binding energy, which binds the nucleus and counteracts the repulsive Coulomb forces between protons. During processes like fission, e.g., the splitting of uranium-235 into barium-141, krypton-92, and neutrons, and fusion, e.g., deuterium and tritium forming helium-4 and a neutron, the mass defect results in significant energy release. This energy appears primarily as the kinetic energy of reaction products, with observed emission patterns and recoil effects indicating a powerful, localized release within the nucleus. The high kinetic energies of reaction fragments, their opposing emission directions, the inverse relationship between fragment mass and velocity, and significant recoil effects all resemble an explosion. These characteristics suggest that the missing mass may undergo a phase transition into a novel form of fine matter, rather than being directly converted into energy. The proposed hypothesis posits that the mass defect induces an explosive transformation into a superfine form of matter, transferring kinetic energy to the reaction fragments rather than following the conventional model of mass energy conversion. While Coulomb repulsion and quantum tunneling likely contribute to the observed kinetic energy, this new hypothesis challenges mass energy equivalence by proposing that energy release associated with mass defects results from an explosive transformation of mass. The occurrence of mass defects appears to be a universal phenomenon. Large-scale examples include energy-producing stars, supernovae, neutron star collisions, and black hole mergers, all of which involve substantial mass defects. This suggests that space itself may be infused with this fine matter, challenging the notion of a true vacuum and raising the possibility that phenomena like gravitational lensing and time dilation could result from interactions with this pervasive matter. For instance, dense concentrations of fine matter around massive objects, drawn by gravitational attraction, may influence the speed of light and contribute to observed light bending near stars. Additionally, this fine matter could offer alternative explanations for relativistic effects such as length contraction and mass increase with velocity, as moving objects may experience resistive drag within this medium. This framework has the potential to reshape our understanding of nuclear energy release, cosmic phenomena, and relativistic effects, presenting an alternative to traditional models based on mass energy equivalence and special relativity.